from University of Quebec and Montreal, and he will speak to us on a Cartesian closed category of algebraic theories.
Thank you very much, Dorette. I should apologize for being late this morning. There was a technical problem with my computer just a few minutes before starting. So I'm happy here. I can start now. I will. So this is a title, a Cartesian closed category of algebraic theories, and this is a joint work with Marcelo Fiore. Our goal is to show that the category of algebraic theories and combinatorial functors is Cartesian closed. When I say algebraic theories, I mean unsorted algebraic theories in the sense that you just have a category with finite product, not necessarily with a generating object as in Lorvier theory. So we don't suppose that there is a generating object, just a category with finite product. And also, we will introduce notions of combinatorial functor between algebraic theories, which is not something which is not really in the literature. And with this notions of functors, we prove that the category is Cartesian closed, which maybe is interesting from my point of view. Okay, so okay, so I have 3 parts. 1, 2, 3. I first recall what is a Cartesian closed category, and in the second part I will recall the theory of classical theory of algebraic theories and models and etc. And also recall that the category of algebraic theories is actually symmetric monoidal closed. And in the last part will be about the fact that if you modify the morphism between algebraic theories, you actually get a Cartesian closed category. Okay, so recall the category is said to be Cartesian if it has finite Cartesian products. And a Cartesian category is said to be closed if the product functors with an object A of C has a right adjoint for every object A. And the Hom object, okay, I will often denoted bracket AB, or B exponent A is often called the space of maps or the function space. It was very much studied by Dana Scott, and also Martin Allen, I think, has introduced this terminology of function space. Sometime B exponent A exists for some A and some B, or maybe for all B for a given A, and then you say that A is exponentiable. The exponentiable objects in a Cartesian category has been studied a lot. Susan Neafield, for example, who is going to speak at this meeting, has things to say about exponentiable object in certain categories. Now, an important thing here in this adjunction between the product and the exponentiation is, of course, called the evaluation map, which is actually the co-unit of the adjunction. So, example, the category of set is Cartesian closed. In this case, the function space between two sets is the set of all maps between A and B. And the evaluation is just what you would call the evaluation. You evaluate a map F at an element X by just computing the value. Another example is the category cat, and the category of a small category. Where a morphism is a functor. This is, of course, very well known. The function space between two small categories is the category of all functors from C to D. And a morphism in this category actually is a natural transformation. And the evaluation functor is what you expect. You evaluate a functor f at an object A of C. So this is very classical. Now, I recall what is an algebraic theory in a sort of generalized sense. It's defined to be a small category A with a finite Cartesian product. And we say that a functor between algebraic theory is algebraic. This is just a terminology. If it preserves finite Cartesian product, it's sort of shorter to say that the functor is algebraic than to say that it preserves finite Cartesian product. So we choose, at least for the start, this terminology. The category of algebraic theories and algebraic functor has the structure of a two category, which means that the category of algebraic functors from A to B is, of course, a category. There are null transformation between functors from A to B. So you just take the two cells of this two category as the natural transformation. Okay, now a model of an algebraic theory A is a functor preserving finite Cartesian product from A to Z. You see, it could be defined to be an algebraic functor, I could say. But since set is a large category, I make a distinction between a small category with finite product and a large category like set. So set is not regarded here as an algebraic theory. Now, a morphism between two models is a natural transformation. And so there is a category, we shall denote the category of models of an algebraic theory A by mod A. This is the category of functors preserving finite product from A to Z. And examples of this is a representable functor. And it happens to preserve finite product. And you get the unidad functor that goes from the opposite of A to the category of models of A. So this was very well explained in the thesis of Lauvier in 1963. It's one of the very beautiful work in category theory. Okay, so now I recall that the category of models of an algebraic theory A has limits and co-limits. And also, if you have an algebraic functor between two algebraic theories, you can use it to pull back a model of B to a model of A just by composing with U, and you get the pullback functor or the restriction functor. And this functor has a left adjoint called the push forward functor along U lower shriek. So for example, you can get from this, of course, free models of free algebra, things of this sort. That's a special case. Okay, now, first observation, the category of algebraic functors between A and B is itself an algebraic theory because it has finite Cartesian product. In other words, you can, if you have two functors, U and V from A to B that preserve finite products, then you can do the pointwise Cartesian product of U and V because B has Cartesian product. And this happened to be a functor preserving finite product too. And therefore, the category of algebraic functors between A and B is itself an algebraic theory from this point of view. So you get the idea then that maybe this is the internal arm for a Cartesian closed structure, right? Because it's like in the category of small categories where you have that the category of all functors between two categories, two small categories, itself a category. So you have a Cartesian closed structure. So you may expect the first time you see it, oh yeah, well, that must be the internal arm for a Cartesian closed structure. But no, this category is not Cartesian closed. It's because the evaluation functor that you would just spontaneously write down between the algebraic functors from A to B and A does not preserve Cartesian product. Okay. What happened is this, is that is this evaluation functor preserve Cartesian product in each variable separately. That's kind of almost immediate. If you write it down on a piece of paper and you check this, okay, preserve the Cartesian product in each variable separately, meaning that if you fix one of the variable of the functor, then preserve Cartesian product in the other, but it does not preserve Cartesian product jointly. So this evaluation functor is not a morphism of the category of algebraic theories. And so you have to correct that. And you can introduce a tensor product between algebraic theories. If you have A and B2 algebraic theory, the tensor product of A and B is a functor, is an algebraic theory A tensor B equipped with a functor, which preserve Cartesian product in each variable separately, and which is universal. So the definition is very much like defining the Cartesian product, the tensor product of two module or two abelian groups, and it just works. And the tensor product is obtained this way, is currently associative and symmetric. And then you check that the symmetric monoidal two category is actually closed. I think this is a result which is known since quite some time. I didn't have the time to check with the literature because for many years, people would always restrict to unisorted algebraic theory, the way Lovira defined it. And here we only consider we consider general algebraic. So I didn't have the time to check the literature, but certainly that Kelly in his book has very general observation about tensoring category with product or finite limits and etc. And Kelly understood that you always get something in this way, which is actually symmetric monoidal close. And the evaluation functor that you get from the old evaluation functor that you had, which was only preserving product in each variable, now preserve the Cartesian product jointly, because by the very constructions of the tensor product, and you have then symmetric monoidal structure. Okay, so I'm describing this very quickly because I want to contrast it with the Cartesian closed structure that we are going to describe on a sort of modification of the category of algebraic theories by introducing new morphism. So the main goal is to construct Cartesian closed category C having the same object, but where instead of having algebraic functors from A to B, we will use what we call a combinatorial functor from the mod A to mod B. So it's a kind of replacement which look very costly because we are replacing functors from between two small categories by functors between two large categories, mod A and mod B. But we will see that the category of combinatorial functors from mod A to mod B is actually the category of models of an algebraic theory. And this is how we will get the internal arm. So I'm sort of inviting you not to be too afraid with this substitution, but because it turned out that it's not too costly in some sense, this substitution. Okay, but what is a combinatorial functor? So in order to define what are combinatorial functors, I need to explain what is shifted colimits, and then I will get to the notions of combinatorial functor and etc. etc. Okay, that's the second part of the, or maybe the third part of the. Okay, recall that a small category I is said to be shifted if the colimit functor preserve cartesian product. So this is very similar to the notions of a filtered category. Category I is said to be filtered, or that a possible definition of what a filtered category is just you just ask that the colimit functor it preserves finite limits, but you restrict that to finite product. So a diagram, I recall that a diagram in a category is said to be shifted if the category, the indexing category is shifted, and a colimit, the colimit of a shifted diagram is said to be a shifted colimit. Now, okay, now we are ready to define what is a combinatorial functor. We say that a functor is combinatorial if it preserves shifted colimits. And we shall denote the category of combinatorial functors between E and F by C of FUN EF. And here's examples. If you have an algebraic functor between two algebraic theories, so a functor preserving finite product, then both the pullback and the push-forward functors are combinatorial. It's kind of interesting, but it's a very basic fact of the theory of algebraic theories. Of course, the push-forward functor is preserved shifted colimit because the push-forward functor preserves all colimits. It's a left adjoint. The push-forward functor is a left adjoint, so there is no surprise there. But it's kind of interesting to realize, but it's not difficult to prove, that the pullback functor, which is a right adjoint, preserves shifted colimits. Okay, so again, this is something which was known since a long time. There is no claim here that this is something new, but these are important examples of combinatorial functor. Now, recall that a reflexive graph is just two set with a diagram like this. And it can be regarded as a functor from a small category nabla defined by the diagrams above. And the colimit of this is the co-equalizer of the map. And the co-equalizer is said to be reflexive because you have a common section of D0 and D1. And the colimit of a reflexive graph is actually the set of connected components of G. So now it's very easy to check, even visually, it's almost immediate, that the pi0 functor, the set of components of a graph, the set of components of the Cartesian product of two graphs is the Cartesian product of the set of components. So that means that the category nabla is shifted. And actually, there is a theorem, a functor between co-completing category is combinatorial. That is, preserved shifted colimit, if and only if it preserves directed colimits and reflexive co-equalizer. Okay. And now you could take a category and complete it under shifted colimit. And actually, the unit of functor from A up to mod A is the free completions of A up under shifted colimits. As you may know, A up is the category of finitely generated free algebra in some sense. And every algebra or models of A is a shifted colimits of finitely generated free algebra. And you have this situation where if you take any functor f from A up to E, any functor, it does not have to preserve finite coproduct because A up has finite coproduct since A has finite product. Any functor with value in some category E, let's say co-complete if you like, can be extended uniquely as a combinatorial functor from mod A to E, okay, as a F prime. And now we introduce this category where a morphism between two algebraic theories is a combinatorial functor between the models of A and B respectively. Of course, this category has a structure of a two category where a two cell is a natural transformation. And now observe that if U is an algebraic functor, functor preserving finite product, then the push forward functor is combinatorial because of course it is actually co-continuous, it preserves all colimits. And therefore you have a functor from which I write exclamation mark from the usual category of algebraic theories to the new category of combinatorial C-alg. And well, this functor is behaving well, actually. It takes the Cartesian product of algebraic theories into the Cartesian product in the bigger category. That's because the category of models of A cross B is actually the product of the category models of A and B. So that's a simple observation. And now we need a technical result, is that the category of algebraic theories that, and algebraic functors is enriched over cat. And it can be tensored and co-tensored by cat. It's an important observation, which I trace back to Dubuc because Eduardo Dubuc, because this is, I learned it from Eduardo in his book on enriched category theory. And it is important in what follow. So what is a co-tensor product of an algebraic theory A by a small category C? It's simply the category of functor from C to A. Well, if A has finite product, the category of functors from C to A has finite product, and you get the co-tensor product. The tensor product is in some sense more interesting, but it's a bit harder. So if you have a small category C, the tensor product of A by C is just a category with finite product C tensor A, or with I write C dot A, equipped with a functor that preserves finite product in the second variable only, because anyway, A has a finite product, but C does not have finite product. So you cannot ask the conditions of preserving the Cartesian product in the first variable. It would not make sense. So you just do impose the condition that is there, and it works. That is the tensor product. And now you then have this these equivalents of category, or you have the tensor, the co-tensor, and etc. These are classical identities that connect the tensor and the co-tensor. And the third one is important because it tells you what are the models of C tensor A. They are just the models of A to the C. In other words, they are diagrams of models of A. So that somehow tell you what is C tensor A, because if you know the models of an algebraic theory, you essentially know the algebraic, what is the algebraic theory. And this formula is telling you what C tensor A does. It is the theory whose models are the diagrams, C index diagrams of models of A. Okay, now let's look at the morphism, the combinatorial functors between between A and B. Well, such a combinatorial functors is determined by its restriction to along unida to finitely free algebra of A because of the result I stated before. I mean, so it's completely determined. There is an equivalence So the category of combinatorial functors from A to B is, by definition, that's the definition I just wrote down. And now that's the same as just a functor from A up to mod B. Now, that's a diagram of models of B. Well, okay, then it must be a model of A up tensor B. Okay, that's a theorem. The category is Cartesian closed with internal arm AB is A up tensor B. That's a theorem. Okay, now maybe a little bit. I would like to say that Marcelo is extending all this theory to from algebraic theories to general KZ doctrine. Actually, you could, for example, replace category with finite product with category with finite limits, and it just works. And more generally, the category of models of a KZ doctrine. And also the fact that the category of free algebraic theories, I mean, if you look, it is actually Cartesian closed. I mean, this is a subcategory of the category of all algebraic theories. And this is also something that is proved in a paper by Zeynep Galal. And she is going to submit her thesis at the end of August, I believe, or it's September. And that's something that will be in her thesis. Also, the category of operads and by module is also Cartesian closed by a result of Nicola Gambino and myself, and also Fiore Gambino Island and Wenscale. So there's a whole series of results along the same line, which is kind of developing. And I think the basic result about that was the original result of Fiore, Gambino Island, and Wenscale, showing that the category of symmetric sequence, in some sense, is Cartesian closed. And from that, you can develop other things. Okay, thank you for your attention. Yeah.
Let's thank our speaker. Beautiful talk. Are there questions? You can raise your hand or just unmute yourself.
I'm happy to break the ice again, but I hope for more questions later, so that mine's not the only one. André, thanks a lot for your talk. So my question is regarding one of your last formulas, where you wrote the hom of AB as a tensor. So there's a clear similarity there with the tensor of the dual of a vector space with B. Like you have that same formula in general for, say, finite dimensional vector spaces. And I was wondering if you could tell us more about that.
Martin, I'm very sorry. My ears are very, very bad. They are getting worse and worse. I need to use that. But even with earphone, I was not able to understand your.
I can rephrase, of course.
Maybe we could have this conversation later. But you can, if you don't, of course. But you will. It's 11:05. Maybe there's one more speaker coming in. So I wonder, maybe we can have
there is one more speaker, but the fourth speaker is not here, so we have a little bit of extra time.
Okay, okay. So if you don't mind repeating your questions, but I'm not sure I will be able to. Okay, let's try.
Of course, I'll give it one more try. Thanks.
Okay.
Could you please go to the slide where you wrote the hom of AB as a tensor?
This
there.
one?
Yeah, that one there, like in the theorem.
Okay.
So there's kind of a similarity with the formula, say, for finite dimensional vector spaces.
Yeah, right.
With the dual and the tensor.
Well, thank you for asking the question, because it's a good one. It's kind of surprising, right? But there are differences, of course, between the two. Is that first, the tensor in the middle is an external tensor product. It's not an internal tensor product between algebraic theories. Okay, so the A up there is really just a category. It's not a category with finite product. When you tensor like this, the left-hand side is playing the role of a category. It's not a category with finite product. So if I go back to the definition of the tensor, okay, of this tensor product with a circle dot, you see that this is equipped with a functor preserving finite product in a second variable, and which is universal. So even if C has finite product, this C tensor A ignore the finite product of C. So so it's a kind of strange formulas because it looks like something is hiding, that maybe we miss something, and maybe there is something like a compact closed category there, but we have not been able to find one. It's just that it's the same kind of formulas coming in with A up in addition, which is like the dual. But no, it's not. Yeah, there are strange things in mathematics like this. There are strange similarities that you cannot be easily explained. Just observe that it works. Yeah, it's one of them. I cannot explain it.
And we have a question from Matthias Manny.
Professor Joyal, your
Hello.
definition.
Hello, Matthias.
Hello. Your definition of combinatorial morphism immediately suggests the category whose objects are categories with shifted colimits and whose morphisms are combinatorial morphisms in your sense. What do you know of this category?
Abstractly, well, look, it's a category which is cooked up to get the so as to get the Cartesian closeness. It does not come really some kind of deep philosophy, you know, that we are working by n. It happens that if we define the morphism like this, then suddenly everything works. So let's do it. Maybe Marcelo could answer this question better than I do. I cannot really explain that. Yeah, I'm sorry, I cannot. It just worked. Yeah.
And you would say it doesn't work in this larger category.
I'm sorry?
And would you guess that it doesn't work if you take the larger category?
The larger category of all functors, you mean, or something like this?
No, all categories with shifted colimits and combinatorial functors between them.
A good question. Good. Well, that's a good question. Maybe it does. Yeah, right. Yeah, maybe it does. It's a good idea. Yeah, I didn't thought about it. Yeah. Yeah, that would explain, that would give maybe a good answer to your questions. If it works there, then maybe we have an explanation of why it works here. Yeah, but I don't know. Yeah.
Thanks.
Thank you.
And well, let's thank André Joyal again.
Thank you.
Thank you for a very interesting talk.